Welcome to this tutorial on acid-base titrations. We're learning to draw pH curves and choose indicators. Let's start by looking at what reactions occur between acids and bases. If we have a strong acid, such as hydrochloric acid, this will contain H+ and Cl- ions. If we have a strong base, such as sodium hydroxide, this will contain Na+ and OH- ions. And when mixed together, there will be a complete reaction in which the H+ reacts with the OH- to form water, and hence this is a neutralization reaction. The Na+ ions and Cl- ions are neutral spectator ions and not involved in the reaction, so they remain the same after the reaction has taken place. So for this kind of reaction, we're going to have a look at how the pH of a solution will change. We'll look at the pH in the conical flask beneath the burette in an experiment, and how this changes as we add the hydroxide ions into that strong acid. If the hydrochloric acid in the conical flask is 0.1 mole per decimeter cubed, then the starting pH will be 1. Then when we've added enough hydroxide to neutralize the acid, the conical flask won't contain H+ anymore because it's all reacted to form water. And then if we continue to add more OH-, the solution will become more basic. If the sodium hydroxide is 0.1 mole per decimeter cubed as well, then the final pH will be about 13. In fact, it'll be slightly less due to the dilution by the water which was formed during the reaction. The equivalent point is the point at which all of the H+ has just been neutralized, i.e. when the amount of OH- added matches the amount of H+ that was originally in the conical flask. At this point, the pH of the solution will be approximately halfway between the original acidic pH of 1 and the final basic pH of 13, and the midpoint of 1 and 13 is 7, which is what we would expect for a solution containing water and some neutral spectator ions. So in choosing an indicator for this reaction, we would want to use an indicator which changes colour around pH 7, because at this point the pH changes very significantly on addition of only a small amount of the hydroxide ions. It's very sensitive at this point. So we will be able to know accurately exactly how much base is required to neutralize the acid. Let's go on to the reaction between a strong acid and a weak base, for example hydrochloric acid and sodium phenoxide. Once again, there is complete reaction as the PHO- reacts with the H+ to form phenol. And just to clarify, the capital P lowercase h here is shorthand for the phenyl group, so PHO- is a benzene ring with O- on it, and PHOH is a benzene ring with OH on it, which is called phenol. And not that this matters for what we're talking about. What's important here is that we have a strong acid reacting and protonating a weak base. So to start with, we have the H+ ions in the conical flask and the phenoxide ions in the burette. Once again, if the HCl concentration is 0.1 moles per decimeter cubed, then the starting pH is 1. At some point, all of the H+ has been neutralized by the PHO- to form PHOH. And then as we continue to add the PHO-, the solution will become increasingly basic. If the PHO- concentration was 0.1 mole per decimeter cubed, that would give a pH of about 8.5, slightly basic, as you would expect for a weak base. Now the midpoint of these values is around 4.8, so we would choose an indicator which changes colour around this point, around about 5. If we have a reaction of a weak acid with a strong base, then the reaction involves, for example, here I've got the weak base as NH4+ reacting with hydroxide to form water and NH3. The Cl- and Na plus ions are spectators, as always. And once again, this is a complete neutralization reaction. Let's imagine we have the weak acid in the conical flask and the hydroxide is in the burette. And if the NH4Cl concentration is 0.1 mole per decimeter cubed, then the starting pH will be 5.1 because it's a weak acid. You'd need the Ka value to do that calculation. At some point, the weak acid will have been neutralized, and then as more sodium hydroxide is acid, the solution will become more basic again, with a final pH of about 13 if it's 0.1 mole per decimeter cubed sodium hydroxide, slightly under due to dilution for the water formed during the reaction. The point at which the neutralization has just occurred will have taken place at a pH between the starting and final pHs. In this case, 9 is halfway between 5 and 13. Therefore, for the reaction of a weak acid with a strong base, we should use an indicator which changes pH around 9. Finally, we look at the reaction of a weak acid and a weak base. This is the only reaction we've come across which is incomplete, indicated by the equilibrium arrow, which is going to give us some problems. Once again, we'll imagine the acid is in the conical flask and the base is in the burette. The initial pH is around 5 for a 0.1 mole per decimeter cubed solution of the ammonium chloride. At some point there will be the same amount of weak acid and weak base in the conical flask, and if we keep adding the weak base, there will be a final pH of around about 8.5. However, because the reaction was an equilibrium reaction, we don't see a clear equivalence point, so the indicator will change over a range of pH values. Essentially, this titration is not a good idea. So, sort of in conclusion, therefore, you always want to have either a strong acid or a strong base or both in your titration to get a clear equivalence point and an accurate result. In terms of the indicator that you use, you want to use one which will change color at the equivalence point at the steep point of the graph.